Are you ready?
Hi, everyone. My name is Fahad, and the title of my talk is The Impact of Initialization on Decadal Climate Prediction Using GeoSIMultaneous Coupled Climate Model. This work was done in collaboration with people from different institutions that are listed here as authors. So one of the major or key challenges for improving decadal timescale climate prediction or any longer timescale prediction basically is the model inherent bias or systematic bias, but also the model shock at the state of the initial conditions that model is initialized from. So the improper initialization of the coupled climate model can lead to immediate error growth due to the model shock because of the imbalances of the dynamic of that atmospheric and oceanic initial conditions. The scale in multi-year to decadal forecast depends on the properly capturing the phase of low frequency modes that is responsible for predictability in the initial state and on the fidelity in the simulating surface turbulent heat fluxes. On the right side of the figure, it was actually published in 1996 from Bloom that actually shows dynamically balanced state atmospheric condition versus a dynamically imbalanced initial condition state of the atmospheric simulations only. And shows the precipitation, how much high frequency modes are better simulated in the atmospheric conditions. So in this part of the study presented here, aims to understand the sensitivity of dynamical balance initialized of the coupled climate model that were not previously shown in any other studies. So for the model, we are using GeoSIMultaneous coupled climate model that uses CIS4 as a nice model. For the geos, we use approximately 1 degree by 1 degree cube sphere grids that has a 72 vertical levels. For the ocean side, we use MIT GCM, which is lateral cap 1 degree versus 1 degree and has a 50 levels of vertical levels. We've done a series of experiments with different initialization techniques for the predictability of the decadal longer term predictions that uses reanalysis data. For atmosphere, we use MERA2. And for the ocean, we use ocean estimate known as the ECHO. And we know this is a low resolution to do any kind of longer term prediction, but this is sort of like a framework to do some sort of sensitivity experiment to create a framework so that we can use that for high resolution decadal climate prediction run in the future. So we've done a couple of experiments, but here I'm going to show due to time constraint those 2 experiments. The first experiments, we initialize our model with MERA2 and ECHO initial conditions just as it is. So we take the initial condition. We start from 2005 May, we run a 1 year of experiment. In the second experiment, or we do a replay nudging experiment, which is the replay experiment, we call it the replay, but it's similar to the nudging approach. In the couple model, we constrain the atmosphere to MERA2 initial conditions and MERA2 state in the replay experiment, and we carry out forecasts taken from initial conditions from that replay experiment. But in the ocean side, the SST is not towards an observation state. However, the level below the surface of SST is actually free running in the ocean. So the replay experiments are similar to nudging experiments where replay utilizes an incremental analysis update or IAU process. The replay experiment nudges atmospheric variables toward reanalysis, including aerosol, and the land model is driven with observed precipitation. For in the case of second experiment, we instead of starting from 2005 May, we go back to 2005 February. We run 3 months of replay experiment. We get initial condition from 2005 May and take that initial condition run to another forecast, just the same as the first experiment. So this is a flow chart basically shows how we do IAU and replay at GMAO. So for example, if we start our model at 3Z third hour of the day, we run a 3 hours forecast to go to 6Z. We perform analysis and calculate increment, which is basically analysis minus forecast. We go back to 3Z and we run a 6 hour simulation that applies the increment from that calculation. So we went to 9Z. So from 9Z, we do the same similar thing, basically do a 3 hour forecast, 9Z to 12Z, calculate increment, go back to 9Z and run another 6 hours of forecast. Not forecast, basically apply the increment for the simulations. For the replay, we do similar analysis, but instead of performing analysis, we read in a pre-computed reanalysis data. For example, in our cases, it was a MERA2 data. So we basically calculate increment based on MERA2 data and apply increments to model to do our simulation in the replay experiment. So replay and IAU basically minimizes the excitation of high frequency modes by analyzing increment and dynamically balances our ocean atmospheric state.
So meantime, so we can ask some questions to him if you have so far, right? Yeah. Guessing the results of his talk. Probably you want to show some like improvements of the prediction scheme.
I mean, I
right?
can take question if anyone has
Yeah.
questions.
So, or you can talk without slides, you know. I think that's maybe one solutions. So in your replay experiment, so you only nudged the model's SSTs in the oceans. The subsurface ocean you didn't touch.
Right. So in the ocean side, we do only SST nudging to any observed state, but in the below surface, basically, it's a free running model. So we do have a dynamically balanced atmospheric ocean, but ocean is free running.
Okay, I see.
SST.
Okay. So, okay.
Hello, everyone. We're back. So I was just explaining how we do IAU and replay. So in replay, the difference between IAU and replay is that we, instead of calculating the increment analysis, we do use the pre-computed analysis. For example, we use Mera2 in this case, and we go back to our 3Z and we basically apply that increment and do that, our nudging experiment or replay experiment. So these are forecast results from latent heat flux from those two experiments that I'm just explaining. The top left is from experiment 1, which is initialized from Mera to echo initial condition, and the replay experiment forecast is experiment 2, and the difference between those two experiments are in the bottom panel. So this is a mean state from the forecast, and there is definitely a difference between those two experiments, just initializing from Mera to echo and replay forecast. However, it is improving the replay forecast. However, I don't think that it is substantially improved when you compare to Mera2. So I don't think in the replay to forecast compared to Mera2 initial condition, it is not substantially improved to say that, okay, our initial condition actually improved the mean state of this. So if we're not seeing in the improvement in the mean state, where we see the difference with this type of initialization of the model. So this is a first month of the forecast in the latent heat flux from North Atlantic Ocean. The blue line and red line are from those two experiments. So our blue line is from Mera to echo initial condition forecast, or the replay forecast are shown as the red line. And the North Atlantic Ocean, the associated grid points that taken average are shown as the light colors. So if you see that they started from very similar state initially, and they ended up converging to end of the month. However, in the blue line, we see very high frequency, sort of like spikes after 9 to 10 days associated with the Mera to echo forecast. So model actually have a model shock to that initial condition, and after 9 to 10 days, we see a high frequency variability that are not shown in the dynamically balanced forecast. So what you're seeing after 9 to 10 days, except not seeing in the next hour or the first, second couple of hours in our forecast from the Mera to echo. So this is because our atmosphere was initialized from a reanalysis data, and reanalysis atmosphere has its own memory, right? So its atmospheric memory kind of starts decreasing after a couple of days, and the ocean memory kicks in. And when that ocean memory kicks in, the dynamic imbalance kind of shows up as a high variability spikes in the latent heat flux. Whereas due to ocean and atmosphere is more dynamically balanced in the red line, we don't necessarily have that spikes, and it is more of a more reasonable variability in there. When you compare the Mera2 high frequency variability are very similar to red line. Again, we were looking at the high frequency spikes in there, and blue line obviously has a more unreasonable sort of a high spikes in there. So if you look at the South Indian Ocean, the same figure basically, and we see that the blue line has a more unreasonable high spikes in there. They're very, very unreasonable, like 450 to 500 in like a couple of days, whereas the red line, which is our replay forecast, which is very similar to, in terms of variability, it is similar to Mera2, and we think that it is improved our dynamically balanced forecast. So the take-home message would be the forecast from dynamically balanced initial condition. It reduces the high frequency model associated with the model shocks. So if you look at the forecast from the precipitation side, from different region, top left from ITCZ, top right is from SPCZ, bottom left is from Indian Ocean, and bottom right is from North Pacific Ocean. And same as before, the blue line showing the Mera to echo forecast and the replay forecast are shown as the red line. They're basically top of each other in all of those plots, except the blue line has a sort of like spikes, as I said before, that it creates a very high frequency modes and variability in like a very short time after going a couple of days into the forecast. And these are associated with the model shock that we see, that due to the dynamic imbalances, model has a shock, and after a couple of days, that ocean memory kicks into the atmosphere and forecast from dynamically balanced initial condition, reduces the high frequency modes associated with the model shock. So we have a more stabilized high frequency mode, but what about our longer term climate prediction? Because that's what we talked about. So this is a theta, ocean temperature, potential ocean temperature zonal mean state from the replay experiment on the left. On the right hand side, we have a replay minus echo. Remember when I talked about the model configuration, the SST is nudged to an observed state. However, our below surface ocean is basically free running. So after 3 months, our ocean kind of diverges. So it's not actually close to observed state, although our ocean and atmosphere is dynamically balanced. So what happens is that we take the initial condition and run a forecast. Our low frequency modes such as IPO, PDO, and ENSO are kind of not correctly same phase as our observed state. So we are not going to get the predictability correct. So if we want to do a better predictability, we have to do a ocean atmosphere fully coupled replay experiment so that our ocean and atmosphere have very close to the observed state, but also they are dynamically balanced, and we can run a forecast from there to have an improved predictability. So in summary, dynamically balanced initial conditions for the replay experiment stabilize the couple model and reduce the model shock. High frequency modes related to the surface fluxes are more stable in replay initialized forecast compared to just using reanalysis as an initial condition. To capture the longer term predictability, both atmosphere and ocean initial conditions needs to be dynamically balanced and close to observed state, including deeper ocean levels. The study showed that dynamically balanced initialization can improve the high frequency variability in the coupled model, which was previously not shown in any other than just atmospheric model. So next step would be basically do a couple model initialization with the replay, and we are doing other experiments such as LKTF and adjoint assimilation to modify the initial condition to capture the low frequency modes better, so that we have high longer term predictability for multi-year to decadal forecast. Thank you.
Okay,
thank you for
thank you so much. We might have a question, but we are behind the schedule, so we